Hello students, I hope you are doing good. Today we are going to start our next chapter on first year physics, that is about vectors and equilibrium. So student, this chapter is divided into two major portions. The first half is about vectors and the other half is about equilibrium. Okay, before starting vectors, let us review physical quantities. As we discussed in our last video lectures, that physical quantities are such quantities which can be measured. So we can have many physical quantities like mass, length, time, and we can even have acceleration, right? These were the derived physical quantities, force, momentum, etc. Now, some of these physical quantities, they can be operated easily using ordinary algebra. Like if you want to operate or if you want to add two masses, let's say that we are having a 5 kg mass and we are having another object of mass 10 kilogram, right? Now, when you are going to add such two masses, you can use ordinary algebra and the result will be 15 kg. Okay, that is quite simple, but on the other hand there are some physical quantities which can't be operated using ordinary algebra. They require a new or a different kind of algebra in order to be operated. And because of that reason, physicists divide physical quantities into two categories, and those two categories are vectors and scalars. Scalars are such quantities which can be specified or which can be represented by a magnitude only. We need only a magnitude in order to specify such physical quantities like time, like mass, length, right? So all these quantities are scalar physical quantities. So we can only represent them by using magnitude. They can be specified using magnitude, and magnitude is a number plus a proper unit. In that case, we are having 5 kg, 10 kg, so all these are actually magnitude. Magnitude tells us about the size or the quantity of that physical quantity, right? The amount of quantity of that physical quantity. Okay. Now, on the other hand, we are having vectors. These are such physical quantities which cannot be operated using ordinary algebra. So these requires new or different algebra. Different algebra. Okay. Now, why these kind of physical quantities require different algebra, and on the other hand we are having such quantities which can be operated using ordinary algebra? The reason is some of the quantities, they in order to specify them, they involve another term, that is direction. Without direction we cannot completely specify such physical quantities like acceleration, like force, momentum, velocity, displacement, right? So these physical quantities, due to their directional nature, they require a different algebra, and that algebra in the early 19th century, mathematicians developed such algebra, and that algebra is what we call vector algebra. Vector. We can define vectors as such physical quantities which can be specified by a magnitude and a proper direction. So that's why these quantities can't be operated using ordinary algebra. Like if you want to add two forces, let's say that the first one is 5 Newton and the second one is 10 Newton, you cannot be sure that whether there will be 15, 10 or 5, because you must include the sense of direction in order to operate such physical quantities, right? And for that we need a separate algebra, and that is what we call the vector algebra. Okay, so thus physical quantities have two further categories, vectors and scalars. Scalars are such quantities which can be specified by magnitude only, and vectors are those quantities which can be specified using a magnitude and a direction. Right, so next we will discuss that how we can represent vector quantities. So there are two different ways to represent vector quantities. Let us discuss those two different ways. So two ways to represent vector quantities. The first one is what we call symbolic method. Symbolic representation. Symbolic representation. Okay, so we can represent such physical quantities using different symbols. Like we can use a bold face letter, whether capital or small. So let's take an example. If you want to represent force, we can use F, but we have to bold it. So bold letter can represent a vector quantity, or you can represent acceleration with a small letter, but it has to be bold, right? Okay, I hope it looks like a bold letter. Right, so you can represent a vector symbolically by a bold face letter, or you can use another way to represent it, that is, you can use a simple letter, but you have to place an arrow on that letter. So a simple letter with an arrow above it, like for example, like force can be represented by a simple F, but you have to place an arrow above force or F. Acceleration, momentum with a small letter but an arrow, or you can even represent weight, right? So thus symbolically we can use two different ways to represent vector physical quantities. According to the textbook, we prefer this method. Okay, now what about its magnitude? So this was about the vector itself. In order to represent its magnitude, the magnitude of a vector can be represented by using absolute notation. So you have to place the letter inside absolute notation, like this will be representing the magnitude of force, this will be representing the magnitude of acceleration, right? And for direction, you can simply use a letter and you can place a kind of cap on that letter. So this will be what we call unit vector, right? That we are going to discuss in our upcoming lectures. So these are for directions. Okay, right. So that's how we can symbolically represent vector quantities, right? Next way to represent vector is graphical. representation. Okay, so we can represent vector using an arrow. So it can be represented using an arrow. Now the length of the arrow gives us, let's say if this is force, then we can represent it using an arrow, right? Now the length of the arrow represents its magnitude, and the head of the arrow represents its direction. We can take another example, acceleration in that direction, right? Or momentum in this direction. So the length gives us an idea about its magnitude, and the head of the arrow points toward the direction. So it points toward the direction, right? Okay, using graphical method, if we try to operate different vector quantities, then for that we need a kind of reference frame. In order to operate such physical quantities, we need a reference frame where we can easily and we can completely specify both the direction and magnitude of vector quantities. And that reference frame is what we call Cartesian coordinate plane. So next we are going to discuss Cartesian coordinate system. So in order to represent vector and in order to operate vectors, right? So we need a kind of reference frame, and this reference frame was introduced by a French mathematician in 14th century. And we can completely specify both its magnitude and direction. The magnitude of vector and direction can be specified using such a system. Now what is this Cartesian coordinate system? So it is basically having two lines or two axes, right? So it is the combination of two axes of two mutually perpendicular axes. Mutually perpendicular axis. The first one we call x-axis. It is horizontal, and the other axis we call y-axis, and this axis is vertical. Okay, so let us say that this is the x-axis, right? And the other axis that is perpendicular to the x-axis, what we call the y-axis. So this is the x-axis and this is the y-axis, right? Now these two axes, as we can see, they are mutually perpendicular to one another, and we can have different values depending upon what physical quantities we are going to represent over here, right? So we can have different scalar calibrations, you can say. So this is the origin having coordinate 0, 0, like both x and y at this point they have 0 values, right? So this is the positive y-axis. Okay, what about this one? This is the negative y-axis and this is the negative x-axis. So there will be equally spaced values along x and y-axis. Okay, now let us represent a vector quantity. Let us say that we are going to represent force, right? And in order to represent any physical quantity, the quantity must start from the origin, and this is what we call the reference point, right? So let us say that this is the force, okay, and the length of the force actually shows its magnitude. So if we are having a force of, for example, if we are having a force of 50 Newton, then we can represent such a force on a Cartesian coordinate system. But for that we have to first choose proper scale. So we can take scale like, let's say that 10 Newton is equal to 1 centimeter, then 50 Newton will become equal to 5 centimeter, and then we can draw 5 centimeter arrow, right? Now here this force is making an angle theta with the x-axis, and this theta gives us an idea about the direction of that particular vector quantity. In this case we are having force, right? So it gives us the direction of the force. Now theta can be measured both clockwise or anti-clockwise, but the convention in order to find positive angle theta is anti-clockwise. So we measure theta in this direction, anti-clock. Okay, so if you measure theta clockwise, so you have to take negative values of theta, right? Okay, so this was Cartesian coordinate system. It is very useful because in the coming lecture you will see that how we are going to add vectors using Cartesian coordinate system. We can add 2 or more vectors, right? And even we can find the direction, we can how we can find the angle theta. So all these things we are going to cover in our upcoming lectures. And this is a plane representation of vector. So you can see it is 2-dimensional, right? So it is 2-dimensional. We can even represent a vector in 3-dimensional. For that we have to take another axis, and that axis we call as z, and that would be coming out of this board, right? So if you want to represent a vector in space, then let's say the black marker here, this one is pointing in this direction and its length is representing a kind of vector, then we are having 3 mutually perpendicular axes, x, y and z. So this z will be propagating in that direction. So at that time then the angle will be alpha, beta, gamma. So we are going to cover those things in our upcoming lectures.